Hi everyone, this video is going to be a review of the concepts of heat and temperature at the level of General Chemistry 2. So let's start off thinking about what we mean by heat. So heat in the way that we use it in chemistry is different from the way we use the word heat in everyday life. All right, so in chemistry, the definition of heat is a transfer, and this is the key word, a transfer of thermal energy. And I don't like how I have that up there. I want that all together. Is a transfer, I'm just going to keep saying it until it sticks in your head, of thermal energy from a warmer to a cooler substance. Okay? So you put two things together. One is warmer, one is colder. The warmer object will transfer heat in the form of thermal energy to the cooler object. What do we mean by thermal energy? If you remember back to last semester when we studied gas laws, thermal energy is just this idea that the particles in a substance are moving at a variety of speeds, or they're vibrating if it's a solid. The atoms and the molecules are vibrating or moving at a variety of speeds, and those speeds are faster if the object is hotter, it has a higher temperature, okay? So temperature is going to be defined by how much thermal energy something has. Heat, we're going to reserve that word only for the transfer of that thermal energy from one thing to another. So sometimes you'll hear people say things like heat rises. And what they mean is that warmer air is less dense than cooler air, and so like a balloon, the warmer air will rise to the ceiling in a building. That's not that is not how we're going to use the word heat in chemistry. We're going to be really careful and only reserve it for those times when thermal energy is getting transferred from one thing to another. Okay, so enough of that soapbox. All right, let's think about how we're going to solve problems with this. We're going to use an equation that's going to quantify heat for us. And for reasons that are obscure and you don't need to worry about, heat is symbolized by a lowercase q. This is generally going to be in joules. Sometimes it'll be in kilojoules because it's easier to express that way, but this equation is going to give it to us in joules, which is just, remember, joules is just a unit of energy, so it's just expressing that thermal energy is another form of energy, so that's all good. C here is a constant for each substance. Each substance has its own constant, and this is called either the specific heat capacity or the specific heat or the heat capacity. Everyone has their kind of favorite ways to say it. I tend to just say heat capacity, but it's really the specific heat capacity. This uppercase C, you have to be given these for substances. The famous one being water is 4.18 joules per grams degree Celsius. But in general, you're going to be provided some kind of chart or some means of solving for the heat capacity if you don't have it. M is the mass, and delta T is the change in temperature. And we're going to find the change in temperature, and this has to be in degrees C, by the way. We're going to find the change in temperature. The delta T is always going to be the final temperature, T final, minus the initial temperature. Right? So it's always final minus initial to get the delta T. That matters because it changes whether the delta T is positive for an increase in temperature or negative for a decrease. You don't have to worry about whether it is positive or negative. If you just plug it in as final minus initial, it'll always work out and you won't even have to think about it. It'll just happen. Okay? All right. So let's do a simple problem with this in this example here. So how much heat does it take to raise the temperature of 50 grams of water, and I provided you the heat capacity, as I said I would, from room temperature, which is 25 Celsius, to the boiling point of water, at 1 atmosphere, 100 degrees Celsius. Okay? All right, so we're going to use the equation that I just gave you, Q equals Cm delta T. And since the substance is water, we use the heat capacity for water. Incidentally, this grams and Celsius are all in the denominator of this, so sometimes you'll see people write this unit, and you guys know by now that I'm obsessed with units, so So sometimes you'll see the unit written like that, and that's a little more correct, but a lot of times people are lazy and just do the slash. I don't care which one you do, as long as you're consistent and show the units. How much mass do we have? We have 50 grams of water. And our final temperature is 100, and we started initially at 25. So we're going to do 100 minus 25. All right, and that's going to be degrees Celsius. Notice that Celsius cancels, grams cancel. Hooray, we're left in joules. That's the unit of heat, which I just told you. So this is going to be 4.18 times 50 times 75, and that's going to come out in joules. So now we dig out our calculators. And that's going to come out to, let's see, we got two significant digits here for the temperature. So this is a Q, I'm sorry. We've got 16,000 joules. The number your calculator spits out is 15,675, but there's only two significant digits, so we're going to round that to 16,000. And as you can see here, you could now just express this as 16 kilojoules, right? Because that would be more convenient. You don't have to, because the problem didn't ask you for specific units, but a lot of times people are more comfortable in kilojoules. People get these numbers and they're like, oh my gosh, I must have done it wrong. No, it's totally fine. A joule is just not that much energy. Okay, so it's what it is. Where this heat capacity number comes from, just by the way, this 4.18, that's the amount of heat it takes to raise 1 gram of water by 1 degree Celsius. Okay, so it's not a lot of energy because you're only raising a gram of water by 1 degree, right? So water happens to have an unusually large heat capacity, as it turns out, but in the scheme of things, 1 joule or 4 joules or 100 joules isn't that much energy. So a lot of our answers are going to come out in thousands of joules, and so kilojoules is sometimes a more comfortable unit for folks. All right, moving on. Okay, so let's think about what we oftentimes call coffee cup calorimetry, mostly because in the lab, we use literal coffee cups for this. It's really just calorimetry, but this is how I think about it because I'm used to doing this in the lab. But let's imagine a problem where you had 100 grams of copper, which I've symbolized with this block of copper here, and we're going to drop it into into a coffee cup. So this is what I'm trying to draw here very badly because I'm a chemist, not an artist. Is a coffee cup with water in it, 100 grams of water. Notice that the copper's at 100, the water's at 0, and we're going to mix them together, and then we're going to ask ourselves, what's the final temperature? The final temperature we record experimentally is 92, and the question we're going to ask is, what's the heat capacity for copper? All right. So this requires us to come up with an equation, which is, or let's think about what's going on here to reach the equation. So all of the heat, so this is at 100 Celsius and the water's at 0. So when we dump this in here, where's the heat going to go? Remember, the heat is the transfer of energy. So heat is going to go from the copper out into the water, right? Because the copper is the warmer substance. It's going to transfer thermal energy to the cooler water, all right? So the trick here is that all of the heat that is lost by the copper is going to be gained by the water, all right? So in other words, the values of Q for the water is going to be numerically equal to the value of Q for the copper, except they're going to be opposite in sign, right? Because one of them is gaining and one of them is losing. You can also think about one of them is going to have a positive delta T, the water. One's going to have a negative delta T, the copper. So if you put a negative sign here, that's going to make this all work out perfectly, all right? And in general, we're going to refer to this equation as Q1 equals negative Q2. And it's only valid if you're in a calorimetry situation. So only if there's no transfer of heat to the surroundings, okay? And by surroundings here, surroundings becomes a loaded word very quickly. But the surroundings here is that we're not losing any heat out of the coffee cup and out into the rest of the world, okay? So there's no heat lost outside of the the coffee cup, all right? And if that's the case, if there's no heat lost, all the heat that's lost by one substance is gained by the other. So they're going to be equal to each other, but opposite in sign, all right? Okay, so now we can solve this problem that we've been given. So let's fill in the left-hand side for water. So again, for water, so this is going to be Cm delta T. For both of these equals Cm delta T. It's just for different substances, right? So the right-hand side will be copper, the left-hand side will be water. So 4.18 joules per gram degree Celsius for the water. The water is 100 grams. Oops, sorry, no. They're both 100 grams, I guess it doesn't matter. So 100 grams of water. The final temperature of the water, both of them have the same final temperature. This is something that is going to be important. So when you put two objects together that are different temperatures, they will wind up at the same temperature at the end, right? And so for both of them, the final temperature is the same, but the copper had an initial temperature of 100 degrees Celsius. I think I messed up setting this problem up. I wanted this to be 92.0. My bad, sorry. Okay, so 92.0. Okay, degrees Celsius. And that's going to be equal to, now on the copper side, we don't know the heat capacity of copper. That's what we're solving for, so we're just going to leave that as C. We've got 100 grams of copper. We've got a final temperature of 92.0 and an initial temperature of 0. So that's easy. Okay, so now we're going to simplify things down here. So what do we get? Let's see. No, let's do the deltas first. So I'm going to leave all my units, which I know is a mess, but bear with me. Times 100 times, this is going to be negative 8.0 Celsius equals negative C times 100 grams, 0.0 grams, times 92.0 Celsius. All right? All right, so now we're trying to isolate the C over here. So we're going to divide both sides by the 100 grams times the 92. And if you wanted to simplify before you did this, you're certainly welcome to do so. It probably would have made this easier, but oh well. Let's see, units, Celsius is going to cancel. Grams is going to cancel. We're going to be left with just that joules per grams degree Celsius, which makes sense because we're solving for heat capacity. And so, let's see, can I slide this up a little bit? Yes, I can. Okay, good. So, let's punch it all in the calculator, okay? So we got 4.18 times 100. Oh, the hundreds cancel out too. Let's save ourselves that trouble, okay? Times negative 8 divided by 92. So, over here, what do I have? Oh, you know what? I should have, here, let's make this easy on ourselves. We're going to divide both sides by negative 100 times 92 because that'll make this positive over here. Okay, now the negatives make each other positive and everybody's positive. So that's a good thing. Okay, so we've got two significant digits. So this is going to be 0.36 joules per gram degree Celsius. Ta-da! All right. So it looks horrible and scary, but it's really not that bad, right? So the next one is more scary. Okay, so the key thing here is this equation Q1 equals negative Q2, only valid for two objects put in contact with one another when there could be no other transfer of heat to anywhere else. All right. Sometimes you'll see this written as Q1 plus Q2 equals 0, which is also fine. Because it just means that all the heat adds up to 0 because nothing is getting transferred out of that coffee cup, okay? I find for me, I find this expression of it, the Q1 equals negative Q2, a little easier. Okay, so I'm going to give you a really challenging practice question on this, and I want you to pause the video and try to work this on your own. It's mostly challenging because there's a lot of algebra, okay? So, and I never filled in the heat capacity for lead. Let's see here. We're just going to make it up, okay? Because we can do that. And then that's going to drive people crazy, but you won't be able to look up the answer. So let's call this 0.52, okay? So in an experiment, 100 grams of lead with a made-up heat capacity at 100 Celsius is combined with 50 grams of water at 0 Celsius. What's the final temperature of the two substances? Okay, so try to work this on your own. If you're not, pause this right now. If you're not sure, I'm going to give a couple hints. Okay, so here are my hints. It says the final temperature of the two substances. So remember, that's going to be the same final temperature for both, right? So both of them are going to have the same, both the water and the lead are going to have the same final temperature, all right? That's my first hint. My second hint is that you're going to use the equation we just came up with in the previous question, Q1 equals negative Q2. And when I solve this in a minute, I'm going to make lead Q1, I'm going to make water Q2. If you want to flip them, go right ahead. You'll get the same answer. Okay, so pause the video, work the problem. All right, here we go. So lots of algebra ahead. You've been warned. Okay, so I'm going to make the one side the lead side and the two side the water side. So I'm going to have Cm delta T for both. So I'm given this imaginary, please, someone's going to email me like, that's not the heat capacity of lead. I know, I just made it up because I didn't feel like going to look it up, okay? It's fine. We're not doing cancer research here. We're trying to understand the science. Okay, and we've got 100 grams of that lead. Okay, and the final temperature we don't know, so we're going to call that T final. Minus the initial temperature for the lead. What was the lead? The lead was at 100. Now we do the water side. So negative heat capacity water. And by now you should be just used to 4.18 for water. And we've only got 50 grams of water. T final we don't know. That's a T. Final minus the initial temperature, which is 0. Oh, well, that was smart of me because that's going to make this next part a lot easier. Okay, so I'm just going to simplify this because T final minus 0 is just T final, right? So, oh, excuse me. All right, so now we're going to do, I'm going to multiply the 0.52 times the 100. And actually, let's see if we can simplify our units down just a little bit here, right? So we've got, on both sides, we've got joules per gram degree Celsius, right? So this cancel, and grams cancel, right? So the only thing left is degrees Celsius. Yay, that's fantastic. Okay, so now 0.52 times 100 is 52. So I've got 52, and that is unitless, times T final, minus 52 times 100, which is 5200 degrees Celsius. That is not right. Yeah, it is, because it's 52 times 100 times 100. Yeah. Okay. La la la. Okay. So I'm trying to do this without a calculator. All right. So now, okay, this one I need a calculator for. So over here on this side, I've got negative 4.18 times 50. That's minus 209. And that is also unitless, and that's times T final. So now we have an algebra trick that we don't normally run into in chemistry very often. We've got T finals on either side here, right? So we got to get those together. So the way we do that is we subtract, let's move this T final over. So we're going to subtract 52 times T final from both sides. And that's going to give us negative 5200 Celsius equals minus 261 times T final. Now we're going to divide both sides by 261. By negative 261, right? Because that's going to make all the negative signs positive. All right, that cancels out. So 5200 divided by 261. Now we got to think about sig figs. So somewhere along here we had 2 sig figs from the T final coefficient here, because we had that for the, which turned into, this would have 2, yeah, that's right, so 2. All right, so T final now is just going to be 5200 divided by 261, rounded to 2 significant digits. That's going to be 20 point, because it's 19.92, blah, 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 blah. All right, so remember the little decimal there makes the 0 significant, so whatever. Okay, so anyway, T final here is going to be 20. All right, so a little extra algebra than normal, but nothing too bad. Maybe stuff you haven't thought about in a while, so but it's good practice for you. So, all right, so the key things here are the things that we combined here, which is Q1, Q2 equals negative 2. Q1 equals negative Q2, valid for things that are in thermal contact without, and they're in some kind of shell that prevents them from losing heat to the outside. And then Q equals Cm delta T, heat capacity times the mass times the change in temperature. All right? And with those two equations, you can solve just about any problem involving objects in contact at different temperature. All right? Leave me any questions in the comments. Get in touch. Thanks for listening. See you soon.